Terminology and stability of nuclei. In this second nuclear physics video, we will continue to describe the atomic nucleus. We start with some important terminology used in nuclear physics and finish with the stability of nuclei. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. We start with nuclear terminology. Nuclei are specified by the atomic number, is the number of protons, and it is designated by the symbol Z. The total number of nucleons, neutrons plus protons in the nucleus, is called the mass number, or sometimes the number of nucleons, and it is designated by the symbol A. The neutron number N equals the number of neutrons in the nucleus. Nuclei with combinations of these three numbers are also called nuclides. The atomic number and the mass number describe any nucleus, as the number of neutrons in a nucleus can be calculated by subtracting the proton number from the nucleon number. So the atomic number, the mass number, and the chemical symbol are used together as a shorthand way of describing any nucleus. The nucleon number A is always written as a superscripted prefix to the chemical symbol, and the atomic number Z is always a subscripted prefix. In short, X is the chemical symbol for the element, A is the mass number, and Z is the atomic number. The neutron number is the difference between the mass number and the atomic number. For example, the chemical symbol N tells us that this element is nitrogen. The superscript 15 is the mass number A, and the subscript 7 is the atomic number Z. The neutron number is the difference between the mass number and the atomic number, namely 15 minus 7. The number of protons in the nucleus determines which element an atom is. That is, Z determines what kind of atom it is. For example, every carbon atom has 6 protons in the nucleus, so we immediately know that Z equals 6. Similarly, every nitrogen atom has 7 protons in the nucleus, so Z equals 7, and every gold atom has 79 protons in the nucleus, Z equals 79. So it is redundant to specify both the symbol of a nucleus and its atomic number Z, as described above, and we often omit the subscript Z because the chemical symbol can always be used to determine Z. So we say carbon 14, nitrogen 15, gold 197. Nuclei of all atoms of a particular element have the same number of protons. Although they all have the same number of protons, they may contain different numbers of neutrons. For example, carbon nuclei always have 6 protons, but they may have 5, 6, 7, 8, 9, or 10 neutrons. Nuclei that contain the same number of protons but different number of neutrons are called isotopes. The two most common isotopes of uranium have mass numbers 235 and 238. Determine the number of neutrons for these isotopes. We know that all atoms of a particular element have the same number of protons, and the atomic number of uranium is 92. So all uranium atom has 92 protons. These two nuclei can be written as follows: uranium 238 has 238 nucleons. The neutron number is the difference between 238 and 92. Uranium 235 has 235 nucleons. The neutron number is the difference between 235 and 92. We know that an atomic nucleus is made up of protons and neutrons. So we could assume that the mass of an atomic nucleus is simply the sum of the masses of the protons and neutrons that make it up. But what physicists observe is that the total mass of a stable nucleus is always less than the sum of the masses of its separate protons and neutrons. The difference between the mass of a nucleus and the sum of the masses of the protons and neutrons that are its constituent particles is called the mass defect. We can put the mass defect in a mathematical way as follows. Let's solve an example to make the theory clearer. This nucleus contains 2 protons and 2 neutrons. We take the formula for the mass defect and substitute the given values above. Pay attention. Now you should be wondering, where has this lost mass disappeared to? What is the meaning of the mass defect? It is here that Einstein's equivalence of mass and energy plays a role. When the nucleons come together to form a nucleus, the mass loss appears as energy. That is, the loss in mass implies that energy is released in this process. The energy released, E, is given by Einstein's mass-energy equation. The mass defect is a measure of the nuclear binding energy which holds the nucleus together. If a nucleus mass was exactly equal to its component's mass, that is, neutrons plus protons, the nucleus could fall apart without any input of energy. Therefore, to be stable, the mass of a nucleus must be less than that of its constituent nucleons, so that energy input is needed to break it apart. In short, to separate a nucleus into protons and neutrons, energy must be delivered to the system. This energy is the nuclear binding energy. The binding energy is equal to the amount of energy released in forming the nucleus and is therefore given by. The nuclear binding energy of the nucleus can be interpreted as the energy that must be added to a nucleus to break it apart into its components. The nuclear binding energy is a measure of how well a nucleus is held together. However, in nuclear physics, a better measure to compare the stability of different nuclides is the binding energy per nucleon. The binding energy per nucleon is defined as the total binding energy of a nucleus divided by A, the total number of nucleons. We can think of binding energy per nucleon as the average energy per nucleon needed to separate a nucleus into its individual nucleons. Let's see one example. We first determine the mass defect of the nucleus. Oxygen-16 has 8 protons and 8 neutrons. We subtract the mass of a nucleus from the mass of 8 protons and 8 neutrons. The mass defect is given as follows. Use Einstein's mass energy equation to determine the binding energy of the nucleus by multiplying the mass defect by c squared. We now divide the binding energy of the nucleus by the number of nucleons to calculate the binding energy per nucleon. Now you must be wondering, I understood the concept of mass defect. I understood that the loss of mass appears as energy for protons and neutrons to come together in the nucleus. But why do nucleons are held together in the nucleus even though protons have positive charges and must undergo very large repulsive electrostatic forces in the nucleus? To answer this, we must analyze the nuclei not only from the point of view of energy, but also from the point of view of the forces that hold them together. If only electrostatic forces between protons were acting, the nucleons would fly away, which is contrary to experience. So, to bind the nucleus together, there must be an attractive force strong enough to overcome the repulsive force between the nuclear protons and to bind both protons and neutrons into the tiny nuclear volume. This new attractive force is called strong nuclear force. Now let's see some features of the strong nuclear force. The strong nuclear force is mainly attractive, and it is stronger than the Coulomb repulsive force within the nucleus. If it were not, stable nuclei would not exist. The strong nuclear force is nearly independent of charge, and it acts between all nuclear particles alike. So the protons attract each other through the strong nuclear force, while repelling each other through electron force. Neutrons, being electrically neutral, only attract other neutrons or protons through the strong nuclear force. The strong nuclear force is a short-range force. It acts only when the distance between nucleons is comparable to the size of the nucleus. The nuclear force shows the property of saturation, which means that nucleons show only limited attraction. That is, each nucleon in a nucleus interacts with only neighboring nucleons instead of all nucleons from one end of the nucleus to the other. Thus, a nucleon can attract only the nearest neighbors and has no influence on other nucleons. If the strong nuclear force had only attractive character, nucleons should come together to form a single mass under its influence. But the average separation between nucleons is constant, resulting in a nuclear volume proportional to the total number of nucleons. The possible explanation is that nuclear forces exhibit attractive character only so long as nucleons are separated through a certain critical distance. Qualitative aspects of strong nuclear force are shown in the figure below. At a nucleon separation of 1 Fermi, which is typical for nucleons within a nucleus, it is a very strong attractive force. The equilibrium position, one with zero force acting, for nucleons in a nucleus is at a separation of about 0.5 Fermi. If nucleons are separated by a distance smaller than 0.5 Fermi, the force is very powerfully repulsive. In other words, Nuclei are not easily squashed as the nucleons will not move close together. If nucleons are separated by a distance greater than 4 Fermi, the strong nuclear force is virtually zero. Now let's discuss the stability of the atomic nuclei. Nuclear stability is a concept that helps to identify the stability of a nuclear species. For example, two isotopes can have different abundances, which means their stability is different. The two main factors that determine nuclear stability are the neutron-proton ratio and the binding energy per unit nucleon. The neutron-proton ratio of an atomic nucleus is the ratio of its number of neutrons to its number of protons, which is a principal factor for determining whether a nucleus is stable. A plot of N versus Z for several stable nuclei is given in the figure below. Note that light nuclei are most stable if they contain equal numbers of protons and neutrons, so that N equals Z. Beyond this, stable nuclei contain more neutrons than protons. This is because the strong nuclear force is a short-range force, and most pairs of protons in large nuclei are far enough apart that the strong nuclear force does not act between them. So electron repulsion dominates over the strong nuclear force and, therefore, instability increases. This means if the nucleus has to be still holding up, then more neutrons, which exert only the attractive strong nuclear force, are required to maintain stability. For very large Z, the repulsive forces between protons cannot be compensated for by the addition of neutrons. Indeed, there are no completely stable nuclides above Z equals 82. Binding energy per unit nucleon is actually the measure of stability of the nucleus. The larger the binding energy per nucleon, the more stable the nucleus is and the greater the work that must be done to remove the nucleon from the nucleus. The figure below shows the measured binding energy per nucleon as a function of A for stable nuclei. Let's see important features of the graph. Excluding the lighter nuclei, the average binding energy per nucleon is about 8 MeV. The curve is slowly varying for A greater than 40, which suggests the nuclear force saturates. In other words, a particular nucleon can interact with only a limited number of other nucleons, which can be viewed as the nearest neighbors, rather than with all the nucleons in the nucleus. Consequently, no matter how many nucleons are present in the nucleus, removing any nucleon involves separating it only from its nearest neighbors. The energy to do so is therefore approximately independent of how many nucleons are present. Note that the curve peaks around mass number A equals 50 and corresponds to the most stable nuclei. Iron nucleus 56 with a binding energy per nucleon equal to 8.8 MeV is one of the most stable nuclides that exist.